Good morning, everyone. I am so happy to be here. My name is Mike Place. I am, in fact, the Director of Engineering at SALT and the Principal Project Maintainer. To see the world in a grain of sand. William Blake told us about this in his poem, The Auguries of Innocence. The point that he was making was that simplicities are enormously complex. Consider the question, how are you today, if you don't believe me? Or consider the phone in your pocket, or what it takes to make a single beat of your own heart. We like to believe that complexity is a problem that is closely aligned with the challenges in our field, when in fact, complexity is an incredibly broad concern that is endemic in every science, in every art, and in every relationship. The nature of this complexity is one of those questions that seems to fold in on itself at every opportunity. So perhaps for us, it is best to begin at the beginning. When we say that our work is complex, what do we mean by that exactly? Do we mean that we've added more machines, more devices to manage? Yes, certainly we do. Do we believe that we have more applications to support? Yes, that's true. Do we believe our teams are growing in size and in scope? Yes. Our companies are requiring us to divine more and more difficult and expansive technical solutions. Complexity is one of those terms that we throw around, the vagaries of which do us a great disservice, and we ought to spend some time unpacking them. For example, how do we know when a system has become complex or less? What is it that we measure? What do you point to that allows you to make a determination like this? The number of moving parts, the number of things that could go wrong, the things that do? The automation and infrastructure space is full of what amounts to a series of near religious debates on topics which some really bright minds have argued about throughout the years. We fought about imperative versus declarative approaches for the representations of systems. We've argued about the criticality of state convergence. We've argued about mutable versus immutable infrastructure and many, many other things. But in recent years, another debate has emerged that seems to eclipse all of the others. And that debate is complexity versus simplicity. Now, we'd like to believe, as a culture of engineers, that all things being equal, that a simple system is better than a complex one. And on that point, I'm hardly in disagreement. However, all things are not equal. Because most of the time, when we start talking about simplicity, what we actually mean is abstraction. And it's been so ever since the beginning of the age of the computer. When assembly became hard for the average programmer to manage, we invented C. And when C was too complex, we invented C++. And when that became too much, we invented high-level languages like Python and Go. The command line proved too challenging for some users, and we represented higher-level concepts in graphical user interfaces. But the point is this: in none of those cases did we actually reduce complexity. Processors are still devices that make error-free calculations at mind-bending speeds. Operating system kernels are still interfacing with hardware in enormously sophisticated ways. And all of this is being done as these devices become smaller and smaller and smaller. And what we do when we imagine that we've made something complex into something simple is we've introduced abstraction to hide the complexity. So one of the questions that we have to continually ask ourselves as practitioners of our craft, and especially so when automation comes into play, is whether or not it's appropriate to hide complexity, and what dangers do we expose ourselves to when we mistake abstraction for complexity. The complexity that we manage is not becoming simpler. We're simply moving farther and farther away from it. We move higher and higher and higher up the software stack. And the demands on the humans who need to stay ostensibly in charge increase and increase and increase. And so we must ask ourselves, how is it that we're going to continue to be able to reason about all of this complexity? What are the reasons that we lump all of these concerns about machine sprawl and application density and microservice segmentation into this bucket of this thing we call complexity? It's not simply that there's more stuff to keep track of, but also that we're reaching our limit of our ability to describe these systems to each other. Because more than ever, we talk to ourselves about the importance of hiring engineers who don't just have top-notch logical skills, but also the ability to communicate effectively. We heard about this yesterday in a wonderful talk from Heather at Pluralsight. As this need for good communication in our engineering ranks rises, we should realize the truth of what's driving this need. Because just one example of how complexity emerges, let's rewind to a simpler time. When there was a simple web application stack, there were 4 levels: Linux, Apache, MySQL, PHP. We called it a LAMP stack. But what strikes me about the LAMP stack, looking back, is not so much how few levels it contained, but the shape of this model. It's a single-dimensional model with the operating system at the bottom and the scripting layer up at the top. Then, after that, things started to get a little bit crazy. It was a little bit like physicists in the 20th century. They were faced with this possibility that we might need to move from this 3-dimensional space of Newtonian physics into the 4-dimensional space of Einsteinian theory of relativity. And then from there, theoretical physicists started to describe what might be as many as 11 or more dimensions. And the problem that we face today is a little bit like the problem that the physicists have faced as they have began to explore a world where many more dimensions have begun to emerge. Because as we build out these application stacks, they're no longer these single-dimensional stacks like a LAMP stack, nor are they 2-dimensional stacks like some application diagrams would lead us to believe. A single application stack now has a security dimension and a monitoring dimension, an infrastructure dimension, and on and on and on. Because when DevOps emerged, thanks to brilliant ideas from Jez Humble and John Allspaw and many other people, one of the principal elements that came out of that was the idea that automation and configuration management systems could function as this kind of linguistic bridge between a development world and an operations world. Because suddenly we could represent infrastructure as code, and that meant that the language could be known to both parties. And as this evolved over time, through this emergence of this ecosystem of more tools, we witnessed the extraordinary need to have cultural change follow in these organizations. It was accompanied by this evolution in our shared language skills, and more specifically, by the type of language support that was needed in order to create this shared understanding of the systems that we managed. And this debate, of course, it falls victim to the lure of a high level of abstraction, as is too often the case. Because were the choices surrounding how we represent complex systems as being very high level, we ask ourselves questions like, well, is it better to manage these systems through a graphical interface or through a CLI? Should we describe the statefulness of how these systems operate in YAML or in Ruby or in Docker files? Should we use an imperative approach? Should we use a declarative approach to describe the state of the system? But in fact, the real question that we have to consider in automation and in the science of building systems at scale is this: how can we model this world in a way that we can understand? Now, our approach at SaltStack, as you know, is to try to say yes whenever possible. Salt succeeds as a common language for the description and realization of infrastructure because we've modeled the way that human language actually works. Ferdinand de Saussure, great Swiss linguist, he showed us the way that language operates as this point-counterpoint between denotation and connotation. He said, connotation is the cultural context of a word. It's the relationship of words to other words in a system. Well, denotation, this idea of denotation, is the strict dictionary meaning, the data type, as it were. So SALT succeeds in the description of complex systems because it allows for the connotative description of systems states, both in relation to each other, right, or systems in relation to each other, as you would have in a problem of orchestration. But also the denotative description of a system, the structural data that describes any given state. And so we've applied what you might call language dialects to this principle. So you can use a serialization format other than YAML, such as JSON or pure Python if you choose to do so. And at the same time, we've built a stateful management system that's of requisites, which are connotative. They allow you to describe not just the elements of these systems, but the relationship of them to each other in the operating system or across the entire infrastructure. And it's in this way that we're trying to reach toward a world in which the building of applications and their operational context becomes possible using just data models. But we also believe that automation must be much more than simply a way to describe a system at rest, because systems are not designed to be at rest. Modern infrastructure is highly dynamic. From scheduled jobs to software deployments to crossing the chasm between anomaly detection and automatic resolution. And we call our approach to this dynamism event-driven infrastructure. This model that we pioneered drew its inspirations from the principles expressed in event-driven software development, where each component in a system is free to emit these events onto a common bus. And each component is free to register as a listener for events on that bus and then take action as they see fit. And in doing so, we can illustrate a path forward for the real management of hyperscale, highly distributed systems. Because the best way to address complexity in these systems that are growing rapidly in size and scope and interdependence is not just to add additional layers of abstraction, but to distribute responsibility across these distributed components. In this model that we call distributed command and control, we don't just add abstraction, but we embrace the complexity that's already inherent in the system. We attempt to view each software stack multidimensionally. A service that offers a REST endpoint might need to hear events from an IDS that warns of an attack that's taking place and automatically adjusts its rate limiting, for example. Or a service might need to listen to events from a continuous deployment framework and pull in new code after hearing about an event that notifies it of the availability of a new software build. So in order to advance automation into the needs of systems that are here, we need to recognize what the driving force is behind distributed systems. It's distributed responsibility. Software stacks that exist today exist in these multiple dimensions all at once. They exist in a dimension of security, a dimension of monitoring, a reliability dimension, and a dimension of application awareness, and on and on and on. Because applications that operate on these stacks in every dimension at once in the manner that they need to be managed is the one that will succeed and keep on succeeding. And we believe so strongly that an event-driven approach, full of data-driven structures, which are connotatively aware of these other services, will allow systems to operate in their own best interest. And this is a model that we think can scale to extraordinary heights. There's a great Buddhist philosopher, thinker, and teacher named Pema Chodron. One of the things that she tells us in her teaching is that so often we believe that in order to achieve peace and tranquility from the noise and the hustle and bustle of life every day in the city, that we must travel up the mountain. We must walk further and further up this mountain and leave the complexity and the chaos of the city far down below. And that when we reach the top, this perfect peace is possible. But what she tells us is, what good is that peace really if the chaos and the complexity remain far down below and remain so far out of reach? To really solve the problems that plague us, we have to come down off the mountain. We have to learn to embrace the complexity that is already with us, Because abstraction might serve as a means of control, but it also serves as a means of moving us farther away from the problem at hand. If we walk up the mountain of abstraction, we must do so without forgetting the nature of the problems that will always be present down below. And so to succeed in the future, we must not shy away from complexity. We must embrace it. We must think deeply about how to model these systems, these applications, these services that we deliver. We must encourage our teams to understand every dimension of the software stacks that we deploy, from security to monitoring to automation. And the automation that we build and design and deliver must in turn exist and operate upon every dimension of these software stacks. And so we arrive at what I think is a fundamental truth, not just about systems management, but about the nature of complexity itself. That our ability to manage complexity depends not just on the tooling that we use to abstract away the difficulty, but also on our ability to understand the complexity that exists underneath these tools. That understanding is dependent not just on the language that we use to communicate with each other about these systems, but indeed about the models that we use to describe the systems themselves. And we at SALT will continue to push the boundaries about how to model complex systems and how to build out patterns of automation that can realize these models. The community that builds SALT and every engineering team inside SaltStack, building SaltStack Enterprise and our other commercial tools, embrace the challenges of a complex world. We do not shy away from these hard problems. We embrace them. We believe in looking at the whole picture. We believe in thinking hard about the messy bits. We believe in giving people the tools and the power to build software that in the past we could only dream of. I'm really, really, really proud of the work that we have all done in this room together. And I hope that we'll continue to move forward together to build the world's best automation software that can bring sanity and peace for life off the mountain, down in the valley, in the chaos of a complex world. Thank you.